So we're going to be looking at dynamic programming. And what is dynamic programming? Well, it's another one of our problem-solving paradigms. And it is similar in some ways to divide and conquer, as well as backtracking. Even sometimes when you have a backtracking solution, you can just modify it very slightly, and suddenly it's dynamic programming. So if you recall in divide and conquer, we first split the problem into smaller independent subproblems, and then we solve each of those recursively, and then at the end we combine them for a solution to our original problem. In dynamic programming, we split the problem into overlapping subproblems. So our original problem is a superset of the subproblem here. And then we solve each of these subproblems recursively, as we did in divide and conquer. And again, we combine the solutions to subproblems into a solution for our original problem. And we don't want to compute the answer for a subproblem multiple times, so we store the result. So the first thing you should do when you have a problem and you're going to apply dynamic programming is you should formulate the problem in terms of smaller versions. And then you turn this formulation into a recursive function. And finally, you add the caching or memoization. And you just memoize the inputs, mapping them to outputs. And then all subsequent calls will be just a lookup. You don't have to do any computation. So here's a template for a dynamic programming function. So we have this map here at top. This is our cache. And we're mapping from a problem, however we choose to represent it, to the result, a value. And then our function accepts as input a problem. And the first thing you want to do is we want to check, is this a base case in the recursive function? And if it is, we just return the value for the base case. Next, we check if we have computed this problem before. So we try to find it in our memory, and if it's there, we return it. Otherwise, we haven't computed it yet, so we have to compute it. So this doesn't have to look like this. This can be maybe you just have two subproblems and you're just adding the results together. But either way, you usually start with some value as a result, and then for each subproblem you change the result by combining it with the result of the subproblem. And at the end, you just put the result in the cache and then return it. So a simple example would be the Fibonacci sequence. So we start with the numbers 1 and 1, and then each number in the sequence is the sum of the previous two. So that's solve finding the nth Fibonacci number with dynamic programming. And since this is just a recurrence relation, which we have for Fibonacci, we can just use the recurrence relation. We have Fibonacci of 1 is 1, Fibonacci of 2 is 1, and then Fibonacci of n is equal to the sum of the previous two. So we turn the formulation into a recursive function. Here we have our base case, or base cases. If n is less than or equal to 2, we return 1. Otherwise, the result is the sum of the previous two Fibonacci numbers, and return it. Once we have this recursive function, we can add the memoization. But first, let's look at the time complexity if we don't memoize. So how does this grow if we always compute the same subproblem multiple times? And in this case, it's almost exponential. Or, sorry, it's exponential. It's almost O of 2 to the power of n. It's actually O of phi to the power of n. Phi is the golden ratio, which you may know, may not. It's common in architecture to use it, especially in Greece, ancient Greece. But it is in fact the ratio between the nth Fibonacci number and the n minus first Fibonacci number. Once you get high enough, this ratio, the ratio of the Fibonacci numbers to adjacent Fibonacci number gets closer and closer to the golden ratio. So it converges to that. Oh, yeah, and as you can see here, from Fib 6, we calculate Fib 4, but we also do it in Fib 5 here. So we want to cut out this whole process. So we memoize it. Right here, we have a problem which is represented by an integer. So we can map from integers to integers. And then here at the end, before returning, we store it in the cache. Note that since our problem is just an integer, we could use an array, because our problem is an integer from 1 up to some number. So let's say the maximum number is 999. Well, then we can just have an array of size 1000. And we initialize it with -1. This is just our way of checking how we computed the results here. This has to be some number that can't occur naturally in the problem. So for the Fibonacci numbers, that's -1, because they're always going to be positive. Then here we can check, is this uninitialized? And if it isn't uninitialized, then we return it. The reason you'd use an array is because even though if you have a hash table as your lookup table and it's constant time, an array is always going to be faster overall. Time complexity may be the same, but the array is going to be faster. So if you can, use an array. So what's the time complexity now after changing this, after memoizing the problems we have solved? So we have n possible inputs, and for each of those, it'll either be computed or returned from memory. And note that each input will only be computed at most once. Since obtaining from memory is O of 1, the time complexity is big O of n times f. So we have n inputs, and then f is the time complexity of computing a single input. In the case of the Fibonacci numbers, we're only adding two numbers together, so that's just a constant amount of work, and the total time complexity is O of n. Let's look at another problem. Maximum sum. So we have an array of integers. They could be negative, positive, or 0. And we want to find the interval with the highest sum. So in the example, you see the highlighted subarray is the answer, and its sum is 13. How would we solve this in general? The most trivial algorithm would be to just select a starting point and an ending point, and then calculate the sum of the values between those indices, and then tracking what the maximum is. That would be a cubic algorithm, so it's not very efficient. We could use the prefix sum, static range sum trick, to calculate each sum in O of 1, and then it's just a quadratic algorithm. But can we do better with dynamic programming?
Why do you say this is cubic?
So you select a starting index, you select an end index. Those are 2 for loops. And then for each, then you loop from the start index to the end index, and you sum up the values there. Then after collecting the sum, you check it. Okay, is this the new maximum? Then you store it. So it's going to be 3 nested for loops. Each can take at most n steps. Okay, so the first step is to formulate. So let's say that max sum of index I is the maximum sum interval in the range 0 to I. So we kind of cut off at the end of our array, and we're solving a smaller version of it. Okay, so our base case is the max of index 0, the max sum of index 0, and either we're gonna take the element there or not. So either our sum starts at 0, or it's the element at index 0. Okay. But now, how do we work with this? How do we find the value of maximum of I? What does max sum of I minus 1 return even? Because if our base case is 0, so if we didn't take the first element, how do we know that when we how do we know that it's part of the solution at the next step? I wouldn't say with this formulation it's easy to combine subproblems. So let's try to change the perspective a bit. So let's make sure that the maximum sum interval here ends at I. So then our base case no longer has the selection of taking the element or not, because our interval has to end at index I. So we have to take the first element here. Then in our recursive step, we either start a new interval, so we drop what's in front of our current index, or we extend it. So here we just take the value at our current index and we drop what's in front of it. Or we take the value at the index before our current index and we extend it. We extend the interval by adding the the value at the current index to it here. Okay, so then we have the max interval, which ends at index I, for all indices in the array. And then to find the answer, we just have to go through all the indices and take the maximum of all the outputs here. Okay, so let's turn this into a function. So we start with noticing that our problem is just an integer, and thus we create an array. And then our base case is I equals 0. So we just return the value at this index. Otherwise, we take the maximum of creating a new interval or extending the one before. Then we can add memoization. So here's another way of tracking whether you've computed a problem. Is you create a Boolean array, and here we call it comp, which just means computed, and you initialize everything to 0 there, so it's false. And then you check, have I computed the value? And at the end of your computation, you set that the value has been computed. And finally, after defining this function, we take the maximum over all interval ends. And remember that if you want to repeat this process for multiple arrays, you have to clear the memory between these problems. Okay, so what's the time complexity of this? We have n inputs to the function. Each input is processed in O one time, and the time complexity of the function is therefore O of n. It's doing all the values. We're going to circle back to a problem we covered in the greedy algorithms, the coin change problem. We're going to solve the case where our denomination is just some set of numbers. So given an array of coin denominations and some amount x, what is the minimum number of coins needed to represent the value x? So how would we use dynamic programming here? Now again, the first step is to formulate the problem. So let's create a function, opt, which takes as input I and x. And this will denote the minimum number of coins that we need to create the value x. If we're only allowed to use coin denominations from, well, the 0th coin denomination, or the 0th coin up to the ith coin. Okay, so a base case if x is less than 0. So this is, for example, if we try to take, if we have the value x and we have a nickel and we try to take a nickel, or we try to use a nickel, then we go to x equals -1. We say that is infinity. So it's kind of an error state. If we reach x equals 0, then the answer is 0. We don't need any coins for that. If we finish all our types of coins and reach -1 for index I, then, and x here is a positive number. It's not 0. So we haven't finished taking or finished giving out all the coins we need. Then the answer is also infinity. So it's another error state. Otherwise, in the general case, suppose we're at the ith coin and we have x coins to give out, or the amount of money we need to give out is x, then we can give out a coin, the ith coin, and then add 1 to our result. And the remaining subproblem will be that we are still at the ith coin, but we have less money left to give out. DI less money, exactly. So we subtract from x DI and solve the same problem. Or we could not give out the coin and move to the next one. So we go to coin I minus 1 and the remaining value is x. The minimum of these two options is the optimal answer. So here we're just trying both possibilities.
So why do you always subtract by the larger coin, or the largest coin?
The largest coin?
So you say opt I of x, and then you say on the first line 1 plus opt I x minus di.
Yeah, so at start you're calling this with the largest index for the largest coin, and you try either removing the coin or just moving on to the next one. So we're kind of iterating through all the coins, and at each step we try taking the coin as often as we want.
Makes sense.
So here we'll define our error value here, infinity, to just be some large number. It just has to be large enough. And then we have our denomination here. So our base cases, x is less than 0, infinity, if I is equal to -1, infinity, and then if x is equal to 0, we have solved the problem correctly or properly, and we return 0. Okay, and then we start with the result being infinity. So if one of these returns infinity, then our answer will still be infinity. Okay, we take the minimum over both possibilities. We then add memoization. Just note here we have a two-dimensional array. because we have two integers. Make sure you have the proper sizes. So here we have 10 coins at max. So we need to have space for 10 values of I here. And then we support coin values up to 10,000 minus 1, of course. So time complexity here, we have n times x possible inputs. And we're only taking the minimum and doing one addition. So this is all constant time. So the total time complexity is just O of n times x.
Is n there the number of coins, or what n is the...
Yeah, n is the number of different types of coins. X is the value that we're trying to create. Okay, so how do we know what coins we used? I mean, it's good to get the minimum number, but it would be nicer if we could know exactly which coins we used. And what you can do is you can store back pointers or some additional information, and you can trace backwards through the states to find the solution. Yeah, I have code to demonstrate this. So here we have here we have decided to store the values in variables and then compare them to see which one's the minimum. And then we know at each step, okay, did we take a coin here at this step? And if A is not less than B, well then we just moved on to the next coin, so we didn't take. And then we can have another function which uses this table here, which we created, to determine, okay, the value here is true. We did take a coin. So we recursively call this function as if we had taken a coin. But first we output the value of the coin in some way. You could add it to a list, or you can just output it directly, as is done here. And so here we have the example. We have 3 coins, and we want to try all the values of x up to 100. And either it's going to be impossible, so the result is infinity, or we have here our function to calculate what steps did we take. So let's run this. Okay, Windows wants to scan the item. Scared of the code. Okay, so here we can see 7, 8, and 9. These are easy cases, and the ones before that are impossible. There's no way of creating 10, 11, 12, and 13. For 14, we can take 7 and 7. 15 is 8 and 7. It's all relatively simple. And then here the easiest way to create 100 is taking 4 9s and then 8 8s. So you have 12 in total. So this is how you reconstruct your answer using dynamic programming. And I'll put this code online. There are some comments to explain what's going on. The next problem I want to look at is the longest increasing subsequence. So if you have an array and the integers is just an array of integers. So what's a subsequence first? So if you just select any number of elements to delete from A, and you imagine you do it, then you have a subsequence of A. So if we choose to delete 1, 1, and 2, then the remaining values are 5, 8, 9, in this order. The order has to be preserved. And then we have that 5, 8, 9 is a subsequence. If we remove 5, 8, 9, and 2, we get 1, 1. So that's a subsequence. The entire array is also a subsequence. An empty array is also a subsequence. 8, 5 is not a subsequence. There is no 5 that comes after an 8 here in this array. 10 is not a subsequence either, because there's no 10 in the array. Now, an increasing subsequence of A is just a subsequence of A where the elements are in strictly increasing order. So, in our sample array, 589 and 189 are the longest increasing subsequences of A. So here we have 589 and 189. Now, how do we compute the length of the longest increasing subsequence? These are essentially just subsets of indices. So there are going to be 2 to the power of n subsequences. And we can just go through all of them. But then processing each subsequence is going to be O of n. And then our algorithm is O of n times 2 to the power of n. And If we only have a second's worth of time, then we can only go up to about 23. So let's try dynamic programming. So, like in the max sum problem, let's let list of I be the longest increasing subsequence of the subarray going from index 0 up to index I. The base case is just having the first element, so the length of that subsequence is 1. So what about the general case? And here we have the same issue as in the maximum sum problem. So let's make the same change we did. So let list of I specifically have to end at I. So it's the range from 0 up to I, but the subsequent must end at I. We don't actually need the base case here. You can just take the max of 1 and then a max over all the possibilities. So let's go through this. The answer at index I is gonna be, so let's say we're constructing it from the from a previous answer. So go through all indices j which are less than I. If the value at index j is less than the value at index I, then we can take the longest increasing subsequence at index j and we can add the value at index I to it. So our answer would be 1 plus list of j. Take the maximum over all j, and then possibly this is empty. This could be an empty set, and then we need to just have 1 as the answer. Okay, so
what's your argument again for the length of of 0 being 1, or like the empty array being of length 1?
the empty array? No, not an empty array. It's so our base case was list of 0, so at index 0. And at index 0, it's always going to be better to just take the value there, because that's going to be that's going to be of size 1, and if you didn't take it, you just have an empty subsequence, which is of length 0. So you can always take at least 1 value.
Right. Yeah, assuming you have a non-empty array.
Yeah. Of course, you should probably base case that. If the array is empty, then the answer is 0. But that's something you do, I think you do outside the dynamic programming. Okay, so how do we do this in code? Well, we have our array, we have our memory, and we initialize it with -1. We didn't have a base case, so we just go straight to checking if it's in memory. And then we loop through all values of j up to I. We check if the value at index j is less than the value at index I. If it is, we can extend that subsequence. We take the longest increasing subsequence at index j, add our value to it, so it extends the sequence by 1, and take the maximum of our previous answer and the new answer. Then store it as a result. Okay, and then as we did in the max sum problem, we just go through all the indices and take the max of the answer at each index. So what's the time complexity? Well, we have n possible inputs. And we have a for loop in there, which can take at most n steps. So each input is computed in O of n time. And therefore the total time complexity is O of n squared. And this will be good enough for n up to 10,000 usually. Maybe a bit less, maybe a bit more.
And one thing about the case, the J, when I calls, if the yes, no, but maybe this page before that, I'm not sure. When you compare to the max case, you are. It's another slide.
Here?
No, it had the this.
Yeah.
I'm not sure if I understood correctly, because if we compare it to a substring, so we have like list I, it checks if index I is larger than, if I understand it, index J. So
Yeah.
I'm
So
wondering, because index J, that could be any index in the subsequence, that would be the largest item in the longest subsequence.
no, this is essentially just a for loop. For all indices j which are less than I, such that the value at index j is less than the value at index I.
Okay. Yeah. It's like I did not see it. I thought I was reading it like mathematics.
Yeah, this is
Like,
essentially a set.
oh, yeah, like
This, we're looking at the set of values which satisfy this condition. And then for each value in that set, take the max of 1 plus list j.
okay.
So this is exactly how we wrote in the code. We looked at all values j less than I, and then we make sure that they fulfill the second condition, that the value at that index is less than the value at the other index. And then we take the maximum.
So if I is larger than the largest j, then you add 1.
If I is larger than the largest j,
In the like the longest subsequence.
if I is larger than the longest subsequence, I is just an index.
What is in the index? That's what.
So A is just our array.
Yeah.
Res will store the length of our longest subsequence at index I once you're done with this loop. And then we store that here.
I guess I'll just have to look at the code better.
What?
I more or less get the gist of it. Just minor details. I was just.
So what is it that you?
I think I was just misunderstanding how the code worked. So then I like got mismatch between what my idea was and how the actual code worked. So it's just I need to look at this and just get rid of the mismatch between the how I understood it and how actually it is done. But I think I understand the general idea, and it will not be a problem.
All right. Yeah. So there is a faster method of computing this. Um, I'll just leave that as an exercise for you to think about. It is very much based on this method, but just improved. Okay, so another problem which actually the strings lecture also covers a bit. Let's look at the longest common subsequence. So the difference with the one in the string lecture and the one here is in the string lecture we were looking at longest common substrings, so they had to be consecutive. Here we can leave gaps. So we're given two arrays and we can have them be character arrays for this purpose. So they're essentially just strings. We want to find the length of the longest subsequence that they have in common. So if you look at the example here, we have the string A and the string B. And we can take A, N, I, N, N, which also occurs in B. So A, N, I, N, skip this A, and N here. And this is the longest subsequence which occurs in both strings. So the answer is 5. And the subsequence itself is A, N, I, N, N. So let's formulate the problem. We'll let LCS of I and j be the length of the longest common subsequence of the strings A0 up to AI and B0 up to BJ. Okay, if we have reached the end of either string, then the answer is 0. So that's this -1 here. We've gone past index 0, so we're done with the string. Yeah, so that leaves you with an empty string and a possibly empty string. Could be non-empty or empty. Either way, the longest common subsequence is going to be 0 in that case. And then the general case, you have 3 options. So the first one, if the characters at index I in A and index j in B match, so if this condition here holds, then we can choose to add that to our subsequence, increasing the answer by 1, and asking, okay, well, what is the answer at indices I minus 1 and j minus 1? We could also skip a letter in the array A. So we reduce I by 1, but keep j the same. Or we could do similarly for B. So we stay at the same spot in array A, so I remains unchanged, and then we reduce j by 1. So this will look like this. We have our base cases, our memoization here, and then we try moving in B. Then we try, okay, what if we move in A? Okay, do the characters match? Well then, let's try taking the character and moving in both strings.
And I guess and for this, you assume like it's the subsequence is continuous, right? There's, unlike the longest subsequence, there's no spaces between.
No, you can have spaces in between.
Okay.
So subsequence means that you can have spaces in between. Substring means there are no spaces. Sometimes people just say, when you're working with an array, something that isn't necessarily a string, they say consecutive subsequence. That means it's a subsequence with no spaces, so it's essentially like a substring. So in this case, we can't leave gaps, and that's why here we can. The optimal answer could be, for example, jumping 3 times in array B, and then we have a gap of 3 characters there, and then maybe we start matching again. But we are trying all possibilities here. So, time complexity. We have n possibilities for index I. We have m possibilities for index j. So in total, n times m possible inputs. Each input is processed in O of 1. And thus the total time complexity is O of n times m. So another thing we can do with dynamic programming is we can use bit masks. So if you recall the bit mask representation of subsets, they are mapped to integers. And this allows us to easily do dynamic programming over subsets. So let's look at a famous problem where this can be applied. The traveling salesman problem. So we have a graph of n vertices, and we have a cost between each pair of these vertices. And we want to find a cycle through all the vertices. So we want to visit every vertex exactly once, so that the sum of these edge costs is minimal. Well, the sum of the edge costs that we select for a cycle, that is. And this problem is NP-hard, so there isn't a polynomial time algorithm that solves it. It's all exponential or worse. And what we could do is we could fix the permutation that we want to try, and do that for all permutations, and we just take the minimum value over all the permutations. But we can only get to around 10, maybe 11 with that, if we have 1 second. So let's try to reach higher by using dynamic programming. So since we go through all the vertices exactly once, we could say that we start at index 0, or vertex 0, that is. And it doesn't change anything for us. So let's formulate a recursive function. We have TSP of I, so index I, and the set S. And that represents the cheapest way to go through all vertices in the graph and back to vertex 0 if we're currently at vertex I and we've already visited the vertices in the set S. So we're tracking which vertices are okay to go to. So our base case is that we are at index I and we have visited all the vertices. And then the answer is the cost of going from vertex I to vertex 0. So we go back home. Okay. The general case, however, is we're at some index I, we have the set S. We go through all the values j which are not in S. So it's all the unvisited vertices. And we take the minimum over that, over the value of the cost of going from vertex I to vertex j, and then recursively calling our TSP function with vertex j, and the union of our original set and the set containing j. So we've added j to our set here. So in code, we have our mem array, which is our cache, and we have n possible values here for the index, and then we need to account for all the possible subsets. So that's 2 to the power of n. We have our cost array. Here we check, is the set all vertices? Then we return the cost from I to the cost of from vertex I to vertex 0. Check the memory. Otherwise, here we start with infinity. We go through all the indices of the vertices. We check, is this vertex already in our set? If it is, we just continue. So we go to the next one. Otherwise, we take the minimum of our current answer so far, or the cost of going to vertex j plus solving the problem from vertex j. And then the optimal solution is simply start at vertex 0 and put vertex 0 in the original set. So our original set is just vertex 0, nothing else. What's the time complexity of this? We have n values for the index. We have 2 to the power of n possible subsets. So n times 2 to the power of n. Each input, we have a for loop going through all the vertices, j. So it's computed in O of n time. And the total time complexity is O of n squared times 2 to the power of n. So now we can take n up to 20. ish. So here's a little joke from XKCD on the traveling salesman problem. Yeah, that's it for today. I guess some final remarks. So one way of noticing whether you can use dynamic programming. It takes a bit of practice, but usually in a problem you have some states. You have a state which you can go through, so you can transition from one state to the other. Like in the Fibonacci one, we have to transition to states n-1 and n-2 from the state n. And if your state space, so all your states, and you add in the transition as edges, and these are directed edges, if these form what's known as a directed acyclic graph, or a DAG, then you can use dynamic programming. However, if it is not acyclic, so if there is a cycle, then dynamic programming will not work. And then, yeah, so you have your state space, and your time complexity is usually just going to be the possible number of states. So you see, when we're analyzing time complexity, we always think about what are the possible inputs. So this is your state space. And then you may have time complexity for processing each state, and then the time complexity of the total of all your code is going to be just the product of these two. And there are some more advanced dynamic programming methods, but I won't be covering them. We don't have the time for that. So I'll just leave it at that. For the problem set today, so there are 5 problems, 2 bonus problems. Canonical coin systems, this is regarding the coin change problem. Global warming is a bonus problem. String stretching is also a bonus problem. This is a more difficult version of the Welcome to CodeJam problem, which was in the problem solving paradigm problem set. And yeah, they are all valued 1 point. You need 3 points for full marks. So are there any questions at the end? Alright, I'm gonna end the lecture here then.